Hi everyone, in this video we are going to do a modified Atwood machine but with multiple objects. Alright, let's get started. So to start off, let's come up with a system. So if you remember, a modified Atwood machine is like an Atwood machine, but the object is on, one of the objects is on a surface. So I'm going to call this, let's call this M1. And M1 is attached to a rope, and the rope hangs over, and there's a secondary object. And we'll call this M2. All right, now with multiple objects, we can have another object hanging off of M2, but what I want to show you is I want to show you the version where we have a object on the other side of M1, kind of like this. M3, right there. Okay, so here we have a Atwood machine, a modified Atwood machine, but in this modified Atwood machine, I'm going to make this a little bit better. We have 3 objects total, where 2 of the objects are on the hanging side. Okay, so the very first thing that you want to do after you give this one a good sketch is you want to create a free body diagram for all 3 objects. So I'm going to do that right now with M1. Now remember, because M1 is on a surface, we have surface forces called the normal force. So that's F of n going up, and of course the force that we should always draw, the force of gravity. I'm going to call that Fg1. To signify that's the weight of mass 1. The other force that we have over here, because we do have 2 strings, I'm going to say the one going to the right, let's call this tension 1. And the one going to the left, I'm going to call this tension 2. Okay. The reason why they're not the same tension is because they're actually different ropes. You had to imagine that the rope that is on the left-hand side is like kind of tied to or knotted onto a hook on M1, and it's not going through M1. And so the rope on the other side, that is a brand new rope compared to the rope on the left. Okay, now let's do a free body diagram for our M2. I'm going to do this one in green. Yeah, so the very first force that we should draw is the force of gravity going down, Fg2, and we have the force of tension going up. Okay, now if you remember, we called this rope T1, so I want to call this T1 as well. And there are no other forces, so I'm going to go over to M3. And for M3, let's do this one in blue. We have the force of gravity going down, Fg3, and this rope, we call it T2, so I'm going to make this T2 as well. Alright, so we have our free body diagram right here. So the next thing that you want to do is you want to identify what the axis of motion is. And what I mean by that is when we release the Atwood machine, what direction is the Atwood machine going to move in? Now, the best way that I found to do this is to look at M1, right? Because M1, it doesn't have the liberty of rotating its axis. It's stuck in that plane. And so M1 will always be moving along the x-axis. And so what we want to do here is we want to adjust all of the masses so that the masses all move along the x-axis. Now, luckily for us, M1 already moves in the x-axis, but we have to adjust M2 and M3. And I'm going to do that by swinging M2, because it's like attached to a pulley, so we can like swing it around. We're going to rotate this up this way to the right, and I'm going to move M3 up this way, and that'll be to the left. Okay, so if you watch the other modified Atwood machine video and the Atwood machine videos, you've seen me do this technique. All right, so after I do that, I'm going to redraw the scenario. I'll do that in the bottom here. And when I redraw the scenario, I want to redraw it with the modified axis of motion. So we have M1 here, string, string, and we're going to call this, what was that, M2? Yep. All right, so we have string here, string, and I believe we call this one M3. Okay. Now I'm going to use this free body diagram above as a reference. So the first M1, we did nothing to change it, so that'll remain as the very same free body diagram. And the left one will be T2. And let's try the modified version of M2. So M2, we see that T1 was going straight up, and the arrowhead was pointing towards this, what do you call this? This pulley right there, this wheel. Okay, so I want to make sure that T1 also follows suit. It's going to be pointing towards that wheel. T1 is going to be pointing towards that wheel. We see FG2 is pointing away from that wheel, so I'm going to do the same as here. FG2 points away from the wheel. Now let's do the same for mass 3. Mass 3, we see T2 is pointing towards the wheel, so we'll make it do like that, and FG3 points away from the wheel, so we can call it FG3, and we'll make it point to the left. All right, so now we have a Atwood machine where everything is adjusted based off of its axis of motion, and once again, everything is moving along the x-axis. That's important here. Next, what we want to do is we want to create a net force formula, and we want to create one for the x and the y. So I'm going to create the one for the x below. So we want to start off with our net force x equation. So f of x is equal to max. And remember, the strategy that I use, I like to go from mass to mass and ask myself, does this force belong in the x-axis? So let's start off with M3 over here. M3, we have FG3, and that is along the x-axis, but it's pointing to the left. Because it's pointing to the left, I'm going to say that is negative. So we have negative FG3, followed by positive T2, followed by, and we're going to go over to M1. M1, we have negative T2 right there. And that's negative because it's pointing to the left. We have positive T1 over there. We're going to go over to M2. So we follow that by positive T1, followed by, excuse me, that should be negative T1. Negative T1, followed by positive FG2. Okay, and that is all equal to the system's mass. So remember how I phrase this? This is the system's mass. And so the system consists of M1 plus M2 plus M3 times the system's acceleration. Right. Now we can clean this up a little bit because we know that T2 cancels out because there's two of them, and one is positive and one is negative. Same with T1. Right. So when we clean this up, we get negative FG3 plus FG2 is equal to M1 plus M2 plus M3 times a sub x. Cool. And at this point, we can rearrange the variables so that you're solving for something. So you can rearrange it so that it's a equals something. But we could even clean this up a little bit more because we know that the weight equation, that is negative M3 times G plus FG2, which is M2G, is equal to M1 plus M2 plus M3 times a sub x. Okay, so yeah, we were able to break it down even more. Now, if you're mathematically inclined, you see that there's a variable of g for both M3 and M2, so we could actually take that out. Let me show you that little trick. So we're going to take out g from both of them, so that leaves us with g out in the front with negative M3 plus M2 times M1 plus M2 plus M3 times the acceleration. So yeah, with this equation, we can even rearrange it even further to find that the acceleration due to gravity would be negative 9.8 or negative 10 for our class, right? It's a cool little trick that we can do. But anyways, the point that you want to get to is at least these two lines right here. With these two lines, you can solve almost every problem, any problem that they give you, because all you have to do after this point is rearrange the variables and then plug in the numbers. All right, next up, we want to do the net force y equation, the net force y equation. Now, luckily for us, for this problem, the net force y equation, we only have to look at M1. So the net force y we have, if we take a look at M1, the only two net force y stuff is f of n, and we have minus fg1 is equal to, now we don't have to include the system's mass here. Well, actually we should, right? Yeah, we should, because we're looking at the system as a whole. So we have m1 plus m2 plus m3 times the acceleration in the y direction. But here's a cool little neat trick that we should be able to pick up. remember, we said it's only moving along the x-axis, and it's only going to be accelerating along the x-axis. So this will be 0, which makes all of this 0 as well. And so we get f of n minus fg1 is equal to 0. And we can rearrange it by saying that the normal force is equal to the weight of the first block right there. Okay, so the important thing here is, are you able to get to this line? Because if you're able to get to that line, then you are golden. Okay, so the one last thing that I want to show you is after you find the acceleration, how can we find the tension? Okay, so how can we find the tension? So you found the acceleration, and let's say we find that the acceleration is, I don't know, let's say m3 is greater than m1 and it's greater than m2, right? So if we take a look at the original image, that means that this object here, m3, is greater than both of m1 and m2. So the entire system is going to be accelerating to the left and kind of like counterclockwise, right? So m3 is going to fall down, m1 is going to move to the left, and m2 is going to rise up. All right. So we find that, and we find the acceleration, whatever that is. So next, what I want you to do is, are you able to find the tension? Okay, can you find the tension? Now, this is how we can find the tension. First, you want to always be able to find the acceleration. All right. So if we were to do how to find tension, okay, how to find tension. Step 1, find the acceleration. So once you find the acceleration, the rest of the problem actually comes very cleanly together. So let's say we want to find what T2 is. So in order to find T2, ignore the rest of the system, but only look at whatever object is attached to T2. So in this case, it'll be M3. So I'm going to focus on M3 right here. Okay, so there, I want to create a net force equation. And that net force equation, F equals ma, we have negative fg3, negative because it's pointing to the left, plus t2. Now, the reason why I'm saying it's negative and it's to the left is we want to make sure that we keep these all like, we're using the same notation throughout. That way, mathematically, things don't get like tricky and it doesn't go all haywire on us. All right, so we have negative fg3 because it's pointing to the left plus t2 times the acceleration. Now, we want to find the tension. So what we can do is we can move fg3 over on the other side to find that t2 is equal to m3 times the acceleration plus fg3. Okay, and we could break this down even more by saying it's m3a plus m3 times g. Okay, so we have this equation. So if I want to clean it up below, I want to write something like this. T2 is equal to m3a plus m3g. Okay, I'm just rewriting what we wrote over here. And from here, as long as you found the acceleration, if we take a look over here, step 1 is find the acceleration. As long as you find the acceleration, you just have to plug in that acceleration value right there for deceleration. Now, if you are trying to find this in variable form only, look what we can do. Okay, we know that it's accelerating, and we found the acceleration over here. Right, we can rearrange the equation so acceleration is equal to something. So after you do that, whatever that is equal to, you could just plug it in right in there for the tension equation, and we're going to actually find the value there. Okay, so in order to find tension, remember, step 1, always find the acceleration. Step 2, you want to isolate a mass with the tension, okay, and only look at that one, and then you want to be able to finally solve. All right, so that is a modified Atwood machine with multiple objects. I'll see you next time.